Hello everyone, I am Dr. Sachida Nansen, working as Associate Professor in the Department of EEE School of Engineering, SR University, Warangal. So we are coming here for the lecture number 10th, which is regarding the emerging trends in battery management systems. So let us recap whatever we have learned till now in this domain regarding the traditional BMS functions. So how it has evolved in the upcoming future, how the plannings have been done, how design implementations can be done, where lot of improvement or innovations can be incorporated. All those aspects we are going to see today. So monitoring, so cell voltages, temperature, current, these are the crucial parameters that need to be monitored. In state estimation, what are the things which are, we are estimating those things which are not measurable. So the parameters like state of charge of the battery, state of health of the battery, then state of functionality. It is although related to state of health only, what is the operational status of the battery, how much efficiently it is working or not. So then other things coming to the protection part. So over voltage protection is there, under voltage protection, over current and over temperature. So in over temperature means it is this subsystem within the battery management system is there, that is called thermal management system. So it will be definitely using one of the cooling mediums like forced air, then liquid based cooling, okay, fluid based is there, then immersion based is there, then paraffin wax is there, okay, so phase change material. So different techniques are there coming under the cooling of the batteries, that is the thermal management is there. Although there are other protection devices like over voltage, over under voltage and over current. Then balancing, maintaining the voltage uniformity across the cell. So like we have seen the cell balancing, how the state of charge will be able to be transferred from the fully charged battery to a half charged or partially charged battery. So that way we will be able to maintain a uniform state of charge as well as uniform voltages. Then active balancing, passive balancing, those things we have already discussed. Then communication techniques. So I have already mentioned this, that battery management system is a lower level controller, okay, that has to receive instruction from the vehicle controller, okay, centralized vehicle controller, which is at the upper edge, okay, higher in the up in the hierarchy, and it has to share all the data of the battery, okay, corresponding operational status of the battery to the vehicle control unit. It is also called the electronic control unit of the vehicle and charger. So interface with this instrument. Now coming to why emerging trends are needed. Why there is a need that the upgradation should be there in terms of battery management system. What sophisticated software or hardware technology we can implement. So those aspects we are going to see. So first of all, EV packs voltage is growing day by day. So earlier it was 400 to 800, now almost 1000 volts it is going. Similarly, increase in energy density, power and safety requirements. Okay, more and more safety concerns are coming. So companies, government, policies, they are making the compactness, okay, design of the battery, that is they are giving highest priority. So integration, now that electric vehicles are also a part of the charging infrastructure, and charging infrastructure is either receiving power from the grid, okay, or transferring the power back to the grid. So definitely integration with the smart grid, renewable sources and AI based diagnostics are there. Okay, so in that means what happens? We are going for continuous connection of the batteries with these systems, okay, smart grids, renewable sources and AI based diagnostic process we are putting in. Then transition towards the connected, intelligent and autonomous BMS ecosystem. We will see more about these details. So we are gradually shifting towards intelligent, AI based, autonomous decision making based upon the past data collections. We can train the ANN models, okay, and we can give the present data, and it will definitely be able to take proper decision and take proper course of action for the working of the batteries. in a efficient manner. So these are all some of the trending requirements why we are going for upgradation in the BMS, emerging trends. So BMS market context between 24 to 30 will see global battery management systems market was around 8 billion in 2024, and we are in 2026 currently, so maybe it will be around 10 billion, but by 2030 it is expected to be doubling from here. So almost 20 billion, so which is growing at a pace of almost 15% per annum. Compounded annual growth rate. Okay, so CAGR. Then driven by the electric vehicles, stationary storage, drones, marines and aviation applications. Different applications are coming up which are relying upon the use of batteries, efficient batteries for proper operations. Okay, industry leaders like LG Energy, Tesla, BYD, Bosch, and BYD means build it yourself. That I think Chinese brand is there, and Bosch is there. Then TI, Texas Instrument, Nuvation is also some of the brands they are working in towards the battery management systems. Now battery management system as a whole, what we can expect from these things, like BMS is growing around, just now mentioned, 15 to 20% CAGR. Then these are the scenario 9.56. This is increasing industry development. Okay, contemporary MPRX Technology Company Limited, Kettle, introduced an advanced BMS, namely Quilin BMS, so designed for high performance electric vehicles. So trends and development of sustainable batteries is there. Then what are the drivers? Growing adoption of electric vehicles. So day by day people are getting awareness about the cost effective way of commutations or mobility. So they are increasing the dependency towards the electric vehicle and reducing the dependency towards the fossil fuel based or that crude oil based mobility systems. Then expansion of renewable energy storage is also there. So overall the ecosystem is going greener day by day. So in that any type of storage device where BMS is used, like for electric vehicles or stationary storage also, they are also integrating doing innovations in the extended use of the battery management system. So there are 3 different designs we have already discussed, and again maybe we'll see again. So centralized, distributed and modular designs are there. So mainly electric vehicles consume 45% above percentage of the applications of the battery. Rest of the things like consumer electronics, industrial energy storage and all. So by type stationary mobility is there. By battery type nickel, cadmium, solid state lithium acid, lithium ion and lead acid is there. Okay, so these are the different aspects of the battery management system market. So coming to the next generation BMS. So what we are expecting from the present or traditional BMS and where we are having the scope of improvement. Okay. So like third party digital remote monitoring services companies are there who are developing the sensors and they are monitoring the data. So like building controllers, field controller, facility equipment. So here data flow is an open integrated platforms. Okay, this is all about the traditional. It was working like this. Then BMS analytics, AI automation, routines, data lake is there. Okay, so these are leverage cloud computing based systems. So cloud computing based systems. So mobile and reporting apps, then business systems, smart building systems, smart building applications, dashboard and reporting designed for mobility. So these things can be developed. Business related means how much energy you have sold, how much energy you have consumed, so at what price, so the difference will be used to calculate the profit and all. Okay, so different decision making analytics like histogram, pie charts, okay, these bar charts, this will be displayed over the phone to make the decision whether we are willing to sell the stored energy from our EV or not. Everything can be mobile controlled and all. Monitoring can be done continuously. Reporting can be done. Data logging system should be there. So these are all the aspects of broad aspects of the upcoming next generation BMS, which is nothing but a extension of the traditional BMS systems to the more sophisticated, and with the help of remote monitoring and BMS analytics we will be doing that one. So database systems. Now coming to the conventional architecture. So in conventional architecture, they already mentioned there are three broad design, that is centralized BMS, distributed BMS and modular BMS. So in centralized, only one BMS system will be there. Single controller manages all the cells. Okay, local modules with master slave communication will be used for distributed BMS. Okay, small packs, 2 watts electric vehicle, we will be going for central. Centralized is small size because centralized means lot of communication channels or wirings need to be done. Lot of information need to be shared. So if a large size battery pack is there, it won't be feasible for a centralized system to make it operational. Otherwise, lot of communication expense will be there. So for small packs, centralized is suitable. A medium electric vehicle, distributed BMS is suitable, where master and slave. So 4-5 modules combined together, they will be having slave operational, and one master will be there on top of that. So similarly, modular means cluster of independent modules connected to a central gateway. Modern electric vehicles, okay, like Tesla, BYD, these companies are using mostly modular. So as the size, rating or capacity of the battery is increasing, definitely close to 80-100 kilowatt hour, means with the range of the four-wheelers around 550-600 kilometers, definitely they will be going for the modular BMS. And for two-wheelers, mostly centralized is good enough. And mid-size hatchback like 50 kilowatt, 60, 40 like that, it will be suitable for distributed BMS applications. So modular and scalable design. So plug and play modules allow every scaling of different pack sizes, okay, between 10 cells to 1000 cells. So plug and play modules. So simply we can connect and disconnect the battery packs. So allows each scaling at a different pack size, okay. So reduces wiring complexity, improved fault isolations, okay. So Nuvesan BMS, which operates within this much of voltage range. It is minimum is 48 and scalable it can be up to 1000 voltage also, 1000 volts also. Then benefits. So benefit easier maintenance and upgrades. So higher reliability through redundancy. So maintenance will be easier if we are going for modular and scalable design. Higher reliability will be there through redundancy. So redundancy means we are reusing some of the series parallel connection. So some form of redundancy is available in case of modular. So supports flexible pack design, series parallel combinations and all. Okay. Then wireless BMS. So in wireless BMS, what happens? Eliminates the wired communication between the cells, reduces 90% of the wiring. So there is a future generation or next generation BMS architecture. One of them we are discussing is the conventional architecture. Just now we have seen, out of them we have identified the modular and the scalable design is the best suitable. Similarly now, to further reduce the burden, we are going for wireless BMS. In wireless BMS, eliminates the wired communication between the cells, reduces 90% of the wiring. It uses Bluetooth, low energy Bluetooth, low energy BLE or proprietary radio frequencies. Okay, so communication channels which will be used to charge the battery through wireless mechanism. So General Motors Altium platform uses analog devices for wireless battery management systems. So what are the advantages of this wireless battery management system? It is lighter in weight because if the number of wires are removed, it is reduced. So 15 kg in large pack, so up to 15 kg it will be reduced. Similarly, simplified manufacturing and serviceability. So if lot of connections are not there, if there is less chances of short circuit, and definitely manufacturing and service will be, maintenance will be easier. It enhances the real-time monitoring also. In real-time monitoring, parameter estimation and all, voltage and current frequency monitoring will be better. So challenges that we will be having, electromagnetic interference, because the energy is being transferred through wireless, okay, or even the data will be also transferred through wireless. So definitely some kind of interference will be taking place. Data latency, reliability concerns will be coming, security vulnerability will be there. So if communication channels are connected to the servers, so definitely some external hackers, they will also try to jeopardize the system, they will try to hack the system and all. Okay, so that type of care should be also taken into this factor. So traditional BMS system, okay, need to be converted gradually towards the intelligent battery junction box. Okay, intelligent battery junction box. So what happens in that one? So like in cell supervisor unit, this is at the cell level monitoring. Then battery junction box is there. So contractors and fuses are there. Okay, and here each cell is having some bridging communication, DC to DC converter, microcontroller winning, microcontroller unit will be there, ADC will be there. So this is the BMS unit, and here all this need to be connected properly with this junction box. So they need to be further processed in the next layer. Okay, so here you can see a wired connection, how MCU can be wirely connected, and here one transmitter daisy chain transceiver system is there, monitoring device is there. So instead of directly, microcontroller can be used to communicate with the daisy chain over the battery packs. Okay, BMS IC, BMS IC. So any BMS ICs can be able to share the information through the wired connections. Okay, wireless connections. Okay, and here the BLE and microcontroller can be connected with serial peripheral interface. Okay, SPI connection can be possible. Here also any wired connection is done through SPI, serial peripheral interface, and any in between you can have Bluetooth. So this is operating at a low voltage and this is operating at a higher voltage. So this is all about the upgraded BMS, wireless BMS system. Then same things are also shown here, which type of frequency 2.4 gigahertz while wireless BMS network can be used. Okay, and different modules will have different battery packs, how the battery packs will be communicating with the BMS controller subsystem also it is shown here. Okay, so BMS controller system is there, BMS ECU is there. Okay, customer BMS application layer, ADI production switches are there. So this is all about the robust, secure and safe wireless systems. So another way we can also further enhance this process of emerging trends, where we are able to use, instead of simple logical or rule based system, to predictive system. So one of the lectures we have discussed predictive maintenance. So if we are able to integrate AI ML based algorithm, data driven battery management system, so we will be able to implement the predictive system or develop predictive emerging battery management system. So what happens in the traditional BMS system, uses lookup tables and deterministic algorithm, simple step by step sequential rules will be written down, and based upon those rules only some decision will be taken. There won't be any adaptability and all. So emerging BMS systems, what happens, employs data driven and self learning models to predict failures and optimize the performance. So here we are able to predict the failures, data we are receiving continuously, we are upgrading the data, new data are also monitored, stored and used for the training of the AI ML models. So self-learning models will be developed, which will be using the updated data also. So what are the places where we are able to integrate this machine learning application? So state of charge estimation. So in state of charge estimation, LSTM, long short term memory, Kalman and neural network based hybrid estimation techniques can be used, which will be able to reduce the estimation error less than 1%. Okay, similarly state of health predictions can be done using regression algorithm. Regression is nothing but a relationship, finding a relationship between independent and dependent variables. Okay, like system identification or that polynomial fit. Okay, that regression is represented like that. Then Gaussian process, convolutional neural network is also there, where this state of health can be used. The objective can be like forecast the capacity fed, okay, then resistance growth. So state of health, we will be able to forecast all these parameters. Then remaining useful life estimation. So how we will be able to implement reinforcement learning to estimate the remaining useful life. So it will be able to predict the end of life accurately, means how many remaining charge cycles are available or how many longer duration we are having. We can make a guess based upon the our everyday charging and recharging cycles, okay, so that how long this battery will still survive, okay, how long it will be remaining useful. Then fault diagnostic also it is possible to be used, like decision trees. Then support vector machine, this is also used, like here detect abnormal cell behaviors, okay, so extra heating, extra discharging, so such kind of abnormal or anomalies they can be able to identify. Then thermal management, predictive control and machine learning can be integrated to maintain uniform temperature throughout. So all these AIML data driven based battery management systems make the sophisticated, emerging, futuristic BMS. Once these things are able to be developed, so the level up to which the BMS will be useful, the level up to which we are able to accommodate the algorithms sophistication and algorithms complexity, so that the failure rate will be reduced, the life of the battery can be extended further. So all these things can be quite useful. So here we can see there is a suppose intelligent BMS. So what all things that we can add to make a traditional BMS into a convert it into a intelligent BMS. So first we will see the real-time multi-layer communication. So facilitates active communication among the battery pack, smart BMS users and charge devices through parallel computing for dynamic battery management. Then hierarchical sensing and processing. So hierarchical processing is required. As already mentioned, modular design should be there and multiple layer processing can be there, edge, fog and cloud server. So utilizes end edge cloud structure for remote sensing, real-time processing and cloud-based analytics, enhancing the battery management efficiency. This is also one of the important. This coming under the communication and processing skills. Okay. Then adaptive digital twin modeling. So cloud-based digital twin, we can completely replicate the physical battery into digital system where voltage, current, these digital informations can be used for defining the system model. So cloud-based digital twin employs adaptive modeling techniques, providing accurate real-time representation of physical battery behaviors. Okay. Then comprehensive analytic tools. So integrates data-driven methods, AI, machine learning. So any type of analytical tools, blockchain for precise prediction, prognostic and cyber security. So these are useful for that one. Complex, comprehensive analytical toolbox. Then intelligent driving assistance. So cloud stored data enables smart supports, optimizing the charging, driving patterns, okay, different and safety features, enhances the user experience. Then reconfigurable battery pack control. So as already mentioned, if some of the cells are getting damaged, they should be able to isolated and the remaining circuit should be reconfigured in such a manner that it enables dynamic adjustment of modules, cells within the battery pack itself. Okay. Then maximizing the adaptability and performance. They will be able to maximize the adaptability and performance. So by combining all these upgraded components or features into the BMS, we can say we will be able to make the traditional BMS into a emerging BMS, intelligent emerging BMS. So AI example can be like AI based state of health estimation. Already we have discussed this in detail, like we will be requiring the input as voltage, current, temperature, cycle count. These will be the considered as the input. Then model will be long short term memory network. So this will be used for accuracy, will be around 1% of the state health deviation, lab reference will be getting. Okay, deployed in BMS firmware via edge AI modules. Okay, Similarly, cloud and edge data analytics, it can be used for real-time data uploaded via 4G or 5G to battery cloud platforms. Okay, so the batteries companies, they will be providing some services related to the servers which enables fleet-wide prediction maintenance. So fleet, suppose 10, 20, 50 vehicles are moving around. So what will be the status of the battery individual vehicles? They will be able to provide the prediction, proper maintenance and proper movement can be monitored. Then AI-based updated dynamics can be also added for connected vehicles. Okay, so interconnected vehicles can have this updated information also. So Tesla's cloud-based BMS analyzes millions of battery hours to optimize the charging curves, okay, over the air. So a lot of toolboxes or analytical methods are there which are used to cloud and edge data analytics. So here this diagram shows the dynamic working conditions of the EVs. Okay, temperature, charging C rate, experimental validation, HIL testing can be done. Data can be collected at this point. Then experimental data can be fed through the model. So how to develop that ANN model or that toolboxes which will be able to use the BMS or used for advanced BMS. So this is how it can be used. So some experimentation, validated data, HIL based information should be training and data, testing data, they should be trained and tested, and then we will be able to implement them in the real time based upon the error observed. Okay, mean error, mean absolute error, root mean square error. So those things will be help to improve the next models. So solid state battery management. So advanced technologies. Already we have seen what is solid state battery management. So requires new logic, new control logics, okay, based upon the solid state. So solid electrolytes, narrow operating windows will be there. So key challenges will be pressure management, high voltage interference greater than 900 volts, because here liquid electrolyte is not available. So higher voltage interference will means working will be there, interface will be there. Then AI algorithms required for dynamic impedance estimation. So how the impedance will be estimated dynamically, those things also need to be taken care of. It will help to prevent the thermal runaway, like quantum scape. Solid state battery management integrate real-time pressure and iron conductivity sensors. Okay, so this is some of the toolbox which are available for the operation of the solid state battery management systems. Then cloud-based and IoT-based. So anywhere the processing is done at the server level or at the end level also for to receive some form of real-time updates, so that we are having edge plus cloud plus applications. So these are the architecture of the IoT. Okay, so enables, what is the advantage of this one? So IoT means nothing, sensors, perception layer will be there, then network layer, how the data will be transferred, in between some preconditioning and gateway related things will be there. Then after the network layer, we are having the database management system, okay, where the processing and all will be done at the server. Okay, so at the edge level, we can have the edge or the device level itself, some form of computations can also be allowed to happen. Otherwise, it will be transferred to the cloud and cloud computing will be used. And above the cloud computing or the DBMS level, database management level, what we are having is the application layer. We are able to receive the data analytics in a processed outcome, okay, in the form of bar charts, pie charts and all. Okay, so decision making is easier. We are able to monitor through the applications. So remote diagnostics and software updates is there, over the air. So fleet analytics, battery aging trends, we are able to receive that one. Usage optimization is there, smart charging coordination with the grid, this is possible to be done. Then the platforms which are which provide this type of cloud services which we are having is Bosch battery cloud, then ABB ability is there, then Siemens MindSphere is there, then Amazon's Web Service IoT Core is there. So these are some of the important available clouds or servers for different MNCs, or where the battery is being monitored and manufactured. So these things can be done. So BMS for multi-chemistry systems. So multi-chemistry in future EVs will use mixed chemistries. Okay, different components can be assembled, so different varieties of batteries can be used also in a battery pack. So like we can have lithium iron phosphate plus nickel manganese cobalt based lithium packs. So this is also possible. So how to evolve or how to operate such mixed chemistry, so they will have different operational features, so that also need to be taken care, because BMS is the algorithm which is designed, it should be able to handle all the different types of batteries. Okay, if not at a time, but once the calibration is done, it should be able to manage that one. It should be plug and play, effortless adoption should be allowed. So BMS adapts dynamically using chemistry identification algorithms, then adaptive control parameters. So these things are also crucial for BMS. So multi-chemistry systems. So these are showing some of the cloud-based processing. So data collection, thermal management, cell balancing is there. Okay, BMS slave module is there, which will be providing the data from the battery pack and all. Then BMS main module is there. It will be connected to the CAN through the that vehicle control unit. And here cloud will be transferring the data and receiving from the BMS main module. So time series data, field data, test data, estimation, state prediction and all. Monitoring what we are getting, the parameters like voltage, temperature, pressure and all. Controlling command, what it is sending is like controlling commands like charging, discharging. So managing. So this represents the real-time controlling state estimation, energy management, optimization information, all things will be going to the electronic control unit of the vehicle. So this gives the complete representation of the advanced vehicle management system to deal with this sophisticated upcoming requirements. Okay, so cloud-based battery management. So real battery management systems are there, cell monitoring and all will be done. Then battery management unit is there. Okay, voltage, current and temperature and all this is there. Then internet will be used. So IoT gateway is there. Okay, different IoT protocols. So it will be transferring the information to the cloud from the sensors, and then we are running the digital twin or virtual battery management system in the cloud. So optimal state of charge and all can be estimated and predicted, and this is the cloud-based battery management system. So accordingly some decision can be taken. So as cloud is involved, cyber security is coming into the picture, safety and sustainability and cyber security. Then cyber security in BMS. So EVs and grid storage systems connected via CAN or Ethernet are vulnerable to hacking. Okay, if we are connecting through any type of communication channel and we are transferring any the data, definitely some form of hacking is possible, vulnerable to hacking. So secure CAN protocols like ISO 15118, then encryption is there, then intrusion detection system for anomaly recognition is there. So example threats like spoofing, spoofed SOC. So misinformation can be passed, data referring charging, then unauthorized OTA firmware updates can be done. Okay. So these are things that need to be taken care of. And how it can be done, like cryptography can be used to secure and authenticate the process. Programmable, so writing smart contracts that can be run at program without any change or chance of fraud. Immutability, validated BMS or centralized BMS record are not changeable or irreversible. Time stamping should be there. Security, distributed trust, all transactions are endured through maybe blockchain. Ledger management should be there, corresponding nodes. Distributed networks can be fulfilled. Security means removes need for central authority or data network cannot be changed by the attacks. So all these technology based cyber security challenges need to be also adhered to implementation of these techniques. Then some functional safety standards need to be ISO based. Automotive functional safety is there. Then IEC based stationary energy storage system safety compliances need to be taken care of. Real-time fault tolerance BMS controller should be used with redundancy and insulation. Sustainability and circularity, integration of BMS passport regulation should be there. Okay, traceability, each battery should be traceable to the manufactured companies. BMS record life cycle data, so support second life assessment, recycling logistic, enable circular economy by linking BMS data to recycling plants. So these things need to be implemented to improve sustainability and circularity, then functional safety and standards. So same things are shown here, local BMS, data acquisition, embedded processing and all, and cloud-based BMS, what we are expecting, cloud storage will be there, analytical tools will be there, parallel computing, data mining, machine learning. So lot of computer science related algorithms, hardware, servers, okay, data centers, channel, communication channels, battery algorithm, okay, over the air monitoring, remaining useful life prediction, fault diagnostic. So some battery algorithm also will be able to be operated through the cloud. So this is how the advancement in the future trends we can make. So all these things are shown here. So like inducement of the fault, then what is the type of the fault that need to be identified, then harm of the fault that can be identified, and proper decision making can be taken. So these are all the BMS tasks that can be fulfilled at the cloud level by the sophisticated BMS design that we are expecting to have. Okay, so insulation layer broken. Okay, insulation layer broken, then inheritance defects, aging, then inherent inconsistencies, different working conditions. So different things are there. We will not be going into the detail. So this is all about the emerging trends that we can have in the futuristic BMS systems. So this is the last slide. So here we can see the key takeaways that we are having is, so future BMS are nothing but smart, connected, predictive and sustainable. So emerging trends include AI/ML based predictive maintenance, wireless and modular BMS, okay, cloud and IoT integration is used, cyber secure and safety certified control system, circular data integration for end of life. So AI/ML prediction, wireless and modular battery management system that we have seen, cloud and IoT integration we have just now seen. Then cyber security has to be also provided, so that hacking is not that much easy. It should be avoided. Okay, safety concerns, safety certification should be provided. Then circular data integration for end of life management. So these technologies will definitely help to take the EVs, will define the next gen EVs, microgrids and storage networks. So with this I will end this discussion. So thank you.